Hello everybody and welcome to Simple Harmonic Motion Lesson 4. Now in the last lesson we looked at the theory of the simple pendulum and we came up with the simple pendulum equation for the time period, which was t is equal to 2 pi root L over g, where L was the length of the pendulum and g was the acceleration due to gravity. Now in today's video what we're going to be looking at is a different oscillating system. We're going to be looking at the mass on spring system and we're going to be trying to derive the equation for the time period of that system. Now actually the idea behind this derivation is going to be very similar to what we did in the last video. We're going to try to find the resultant force acting in the system and then we're going to equate that to Newton's second law and try and get an equation for acceleration and then work through from there. So here then is an example of a mass on spring system. You can see that we've just got a normal spring with some masses on the bottom. In fact there was 400 grams worth of masses on this when I looked at taking this video. Now the setup is very similar to how we would have done Hooke's law back at GCSE and under the materials section of the year 1 course. The difference here is though that once we've put the masses on and stretched the spring, we can then either displace it slightly up or slightly down and set it into the oscillations that you can see here. So let's just remind ourselves of the basics of a mass on a spring and the basis of Hooke's law before we actually start to look at the oscillating system. So let's just draw a diagram. Bear with me. Okay. So let's just draw the spring first. And this is the unstretched spring. Now that unstretched spring will have a natural length to it. So I'm just going to draw in there, dotted line. To show us the original length of the spring. If now we put a mass, put a force onto it, then the spring will stretch. So there are the masses and the spring has stretched to that position there. The amount that it has stretched by is the distance between the original length and the length that it currently is now. Now, depending on which way you look at it, you see different people using different symbols for the amount that has stretched. In physics, we quite often use X for extension, but we don't want to use X today because we're going to be using X for displacement a little bit later on. So just for now, I'm going to call that delta L, the change in the length. Now if we think about the forces that are acting on, we have the weight of the masses acting down and we have the tension in the spring acting back up. And what Hooke's law tells us is that the force that we're putting on, which in this case will be mg, is equal to K, the spring constant, multiplied by delta L, which is the extension. Now of course the force, as we said, is that weight, so we can therefore write mg is equal to K delta L, and we'll be using that equation a little bit later on. So now that we've reminded ourselves of the basics, we need to move on now to see what happens when this system starts to oscillate. Now, of course, on the last slide, what we did is we defined, at least from the SHM point of view, the equilibrium position. We said that the weight was equal to the spring constant multiplied by that delta L, the extension, and therefore the net force was equal to 0. So the total force, or the resultant force, is equal to 0. Now, for the purposes of this, I'm going to have a look at what happens when the system is above that equilibrium position. So we are, let's just say, at that point there. So at this point, we've now got a vertical displacement. And if I just draw that dotted line on there. So the vertical displacement, which is going to be that displacement there, will be x, and this is now the displacement from the equilibrium position. Now, once again, I just want to consider the forces that are acting on this system. We've still got the weight mg acting down, and we will still have some kind of tension in the spring acting back up. Here though, because the overall extension of the spring is now less than at the equilibrium position, this tension here will be less than the tension in the spring when it was at the equilibrium position. Now, in order to calculate that tension will still be the spring constant multiplied by the effective extension. Now, the effective extension here is between the blue line and the green line, because that's how far it has been extended from its original length. Now, in order to work out that, we're not going to give it a new letter, we're not going to give it a new symbol, we're going to use the ones that we've currently got. And hopefully we can see that black double arrow there that I've got is equal to the red one, delta L, subtract from that the green one, x. So we end up here with delta L minus x. Because then this tension is now less than when we were at the equilibrium position, but the weight mg has stayed exactly the same, we're going to end up with a resultant force, and that resultant force will, hopefully unsurprisingly, be acting back down towards the equilibrium position. We're now in a position where we can get an expression for the resultant force. Now, Fres, remembering that everything up is positive and everything down is negative. We can look at the up forces first, which is the tension. So that's K delta L minus X, and we can subtract from that the weight, which is mg. Now, because the weight mg is going to be greater than the tension there, so that one will be greater, what we're going to end up with is that here the resultant force will end up being negative, but that's exactly what we're expecting, because obviously in physics we look at up being positive and down being negative. So the fact that the weight is greater than K brackets delta L minus X at that point doesn't worry us, because we know we're going to end up with a negative answer as expected. So let's bring that equation over to a new slide then. So F resultant force is equal to K delta L minus X minus mg. Now we've got our expression for the resultant force. This is exactly the same stage that we ended up at with the simple pendulum. All we need to do now is to follow this through, and the equation will fall out the other end. So the first step then, I want to multiply out the brackets, the K bracket delta L minus X that we've got. So that will equal K delta L minus Kx and then obviously we've got to remember to subtract the mg as well. Now at this stage I do just want to bring back the equilibrium equation that we had before, which was mg is equal to k delta L. So that was the equation probably from, what was it now, 2 slides ago, where we looked at the forces in equilibrium. Now what we can see here is we've got k delta L and we've got mg. And crucially, they are subtracted from each other. But of course, because they're the same, because mg is equal to k delta L, these two bits that I've highlighted in blue are the same, and therefore when we subtract one of them from the other, they're going to end up cancelling out. Now just to show you that, we can substitute either way at this point, it doesn't really matter. We could say that this is therefore mg minus kx minus mg, and the mg's cancel out, or of course we could say it's k delta L minus kx and do the substitution the other way around and say k delta L there, and then they still cancel out. Either way then, what we're left with is that the resultant force is equal to minus k multiplied by x, which is the displacement from the equilibrium position. Now at this point the approach we're going to take is almost exactly the same as the last video when we looked at the simple pendulum. Once again we need to assume that mass is constant, and of course the mass on the spring is a constant. We didn't change it at all in the video that we saw earlier. That is therefore a constant, and we can take Newton's second law and the simplified version of Newton's second law, F is equal to ma, and we end up with the equation ma is equal to minus k times x. So once again we are almost there. Let's bring that equation back. Ma is equal to minus kx. Next stage we will divide both sides by the mass, so A is equal to minus k over m times x. Now at this point again hopefully we can now start to see the similarities with the pendulum derivation. We'll bring back the general equation for SHM. A is equal to minus omega squared x, and once again we've got the right format again. We've got acceleration, we've got the negative sign, and we've got the displacement. What we're left with then now is that omega squared is equal to the spring constant divided by the mass. Next stage then we're going to square root, so omega is equal to the square root of k over m, and remember that omega is 2 pi over t is equal to root of k over m. We take the inverse of that, t over 2 pi is equal to root of m over k, and then we multiply both sides by 2 pi. T is equal to 2 pi root of m over k. And there is the equation that we're looking for. So that's the equation for the time period of a mass on spring system. Once again, to define our terms as usual, time period measured in seconds. M is the mass that we have placed on the spring, which will be measured in kilograms, and K is the spring constant. Now for the unit of spring constant, remember Hooke's law, which says F is equal to K multiplied by the extension. I might as well use L again because we used L earlier. We've got Newton's extensions measured in metres, and therefore the spring constant is newtons per metre. So here is the question for this video. A mass of 400 grams is placed on a spring, causing it to extend by 35 centimetres. The system is then displaced and allowed to oscillate. Calculate the time period of oscillations, and again, same as the Simple Pendulum video, firstly on the Earth and then secondly on the Moon, where, as we saw before, the acceleration due to gravity is approximately 1/6 of the acceleration due to gravity on the Earth. So as usual, pause the video, go away, work out your answers, and then come back when you're ready to see me work through them. So let's have a look at the answer to this then. So firstly, we're not explicitly given the spring constant, so we do need to calculate it. So the spring constant comes from F is equal to K delta L, or Kx, but obviously, as I said earlier, I'm trying to avoid X as much as I can in this situation. Obviously that is then mg is equal to K delta L, or in other words, K is equal to mg divided by delta L. Plugging the numbers in, we get 0.4, so remember I've given it you in grams, so we do need to convert, multiplied by 9.81 and then divided by, and again we're in centimetres, so we need to convert that into 0.35 metres. Now that, when we round it, gives us an answer of 11.2 newtons per metre. Now that is a rounded answer, so obviously I'm just going to keep that in my calculator for when I work out the time period of oscillation. Now for the first part then, we go straight into T is equal to 2 pi root m over k, and 2 pi root 0.4 divided by 11.2. That gives us 1.86, etc. on the calculator, 1.868 on the calculator. So I'm going to round that to 1.19 seconds. Now, of course, at that stage, we've done two separate calculations. Some of you, and to be honest, I probably would have taken the same approach, might have done this from a purely algebraic point of view first. And if you did that, then I absolutely don't blame you. What we could have done is we could have taken this spring constant equation here and have substituted it in to the equation here. So let's do that and see what happens. So we end up with T is equal to 2 pi root, I'm going to make this a little bit bigger because we're going to have a few things in there. There's your original m, then divided by mg over delta L. Now at that point we can see that the masses cancel out, and because we've got divided by, this delta L will end up on the top. And what we're left with is 2 pi root delta L over G. It's funny how these equations tend to end up looking quite similar to each other when you start playing around with them. Anyway, when we then plug the numbers in, so 2 pi root of 0.35 over 9.81, funnily enough, we end up with exactly the same answer of 1.19 seconds. Now for part B, unfortunately at this stage I do have to admit that that is a trick question. The reason I've given you is because it's actually a classic way that exam boards will try to catch you out by making you think that for a mass on a spring system it makes a difference. If we look at the equation, so remember T is equal to 2 pi root m over k. Well, k is a constant, it's the spring constant, and m, the mass, well, it's mass, it's not weight, so obviously the mass stays exactly the same regardless of whether we're on the Earth, on the Moon, or anywhere in the universe. So in fact the answer to that is exactly the same, it's 1.19 seconds. Of course, the simple pendulum, as we saw before, it does affect it. It will have an effect depending on where we are in different gravitational fields. And before you start saying, well, hang on a minute, over on the right hand side in blue, we've derived an equation that has got acceleration due to gravity in there. Well, yeah, that's fair enough, but don't forget, when you come back over to this equation over here, this will be a constant and this will be a constant. So therefore, if acceleration due to gravity changes, then the extension will also have changed. And you can see from the equation over there that they are directly proportional to each other as well. So any effect that G in this equation over here will have had the same effect on the extension of the spring in the first place, and therefore this 35 centimeters that we've got up here wouldn't be the same if we'd have taken that to a different planet. So to summarise this video then, we have looked at the theory of the mass on spring system, and we have derived the equation for the time period of the mass on spring system, which is T is equal to 2 pi multiplied by the square root of m over k, where m is the mass on the mass on spring system and k is the spring constant of the spring. So that's it for this video. As usual, thank you for watching, and I'll see you in the next one.